So let's start. So what does it take to bring up a new feature into LLVM? Of course, we start with the implementation. But in this talk, we will focus on other parts of the process and try to catch details that we sometimes forget there. So once we have the implementation, we usually proceed to testing. The main goal of this step is to find as many bugs as possible and fix them as early as possible to reduce burden of fixing them later. Once we have our feature implemented and tested, we proceed to review. And we iterate until we get our patch approved. When it's approved, it's time to commit, so we commit it. But then we still have some work to do even after it. We have to address any issues which emerge with our code after it's committed. So if something is broken, it's our responsibility to fix it. Now this list looks complete, right? Well, what usually comes off the radar is that in every of these steps, we also often need to pay some technical debt that exists in our code before. So for instance, our feature might be completely correct and valid, but it might expose a bug in another path. And we cannot commit our feature because we expose this bug. So we need to first fix it. The problem with technical debt is that often it's very hard to predict how much efforts we will need to spend on fixing it. And ignoring it is also not an option because it keeps accumulating and cripples development even more. So what do we call technical debt? It can take several forms. The most popular ones are the following. The first one is bugs. It's the obvious one. So we committed something, we didn't think about some corner case, and then it broke someone's test. Now, even if the feature is already committed, we have to return to it and fix this bug. There are other forms as well. For instance, non-optimal solutions. We might use a quadratic algorithm instead of a linear one when we think that number of elements is small, but then someone hits that nasty corner case when it's actually very large. And again, we now have to get back to our code and re-implement it basically. And there is one more form of technical debt. It's unfinished solutions. Sometimes we have a temptation to switch to a next task as soon as our solution covers the case we care about. However, if we do this, then later we or someone else in the community will need to actually cover all the cases as well. That is to pay the debt that we created by not finishing solution in the first place. This year I worked on enabling a heuristics for loop unrolling and managed to encounter all these types of technical debt in this process. I think this experience is relevant to most of developers in the LLVM community, so I would like to share it with you. And hopefully we can take some lessons out of it. So what's the new heuristics that I mentioned? This heuristics has the goal of finding better candidates for unrolling, and it does this by analyzing loop body and trying to predict which optimizations will be further triggered if we unroll the loop. We covered this technique on the conference last year, so if you are interested, you are welcome to check out the video from the last year conference called Advances in Loop Analysis Frameworks and Optimizations. So the main goal of this heuristics is to get some performance, but usually we have to pay for it by increased code size, and as a consequence, increased compile time. A reasonable increase in compile time was considered acceptable because we only do this on the highest optimization levels, but still we wanted to keep an eye on the compile time to avoid big regressions. We were very careful with it because compile time has been a problematic area for LLVM recently. This graph shows average compile time for 10 biggest benchmarks from LLVM test suites for 3 optimization levels, O3, O0, and OS, for last 4 releases of LLVM. That is for last 2 years. And as you can see, we regressed a lot in these 2 years. And we didn't want to make it even worse with our feature. So before enabling it by default, we decided to carry out an extensive set of different various experiments to see how we impact the compile time. So what did we do? Loop unrolling already has some parameters controlling the optimization. And our feature added a couple more. So we took all of them and iterated through a wide range of possible values, measuring compile time and performance for each case. We wanted to see which compile time impact it has, and also find the best values for these thresholds. That is to tune our optimization. But along with these goals, we also had one more important target in mind. We also wanted to find potential problems in our and other passes. When we change aggressiveness of loop unrolling, we start to generate some variations of the tests, which look very similar to the original one, but differ mostly in code size. And if, for instance, we generated a code that twice as bigger as the original one, but we spent 4 times longer compiling it, then we have a problem. This way, we found several places where LLVM uses non-linear algorithms, and some of them, for instance, loop access analysis, is inherently non-linear, so we cannot replace them with something better. But there were also some places where using non-linear algorithms was completely unjustified. And I would like to focus on these places. I have several examples of them. So let's look at these places. And to start with, let's look at path structure. This is a slightly edited code snippet from pathmanagerbuilder.cpp. And usually when we see this code, we expect our passes to be run something like this. So first we do some preparations, we compute missing analysis, and then we run all our passes for all loops, starting from innermost and going to outermost. However, that's not what we had originally. Instead, we had almost every pass in its separate instance of loop path manager, and we kept recomputing analysis in between all the time, which is not very efficient. The reason why this happened was that every loop path had its own set of requirements in terms of analysis, and loop path manager tried to cluster them based on these requirement sets. It was correct thing to do, but not what we wanted. So this year, all the requirements were unified, and now all the passes can actually be merged into a single instance of loop path manager. However, what we ended up with looked like this. So we had less instances of loop path manager, but still not a single one. And now the reason was that we had a simplify CFG in between. Simplify CFG is a function path, and that's why it cannot be scheduled inside the loop path manager. And to fix it, we need to create a loop version of simplify CFG, which we introduced this year, but for now it's not finished, so we are not there yet. We need to finish it first, and then we can finally merge them all together into a single path manager. But that problem was known even before we started our stress testing. And unfortunately, it was not the only problem that we found. We found even more serious and severe problems later in the testing. So to look at them, let's examine preparation step in more details first. So what do we do there? We start from building computing dominance tree. This is required for detecting loops in our control flow graph. Then we convert these loops to a special form, which is more suitable for loop analysis and transformations. And we do this in 2 steps. First, we convert it to so-called LCSSA form. I will explain later what this means, so I won't stop on this now. And also, we convert loops to simplified form. In simplified form, a loop has a dedicated preheader, a single latch, and dedicated exits, which means that the exits can only be reached from this loop. That is, they don't have predecessors other than from this loop. So all this analysis are computed before loop passes, and every loop pass expects them to be valid, which means that every loop pass is also responsible for preserving them. So for instance, if we change If we change control flow graph, then we also need to update dominance tree correspondingly. If we talk about loop unroll, it does change control flow graph. So it also needs to update dominance tree. And originally what we did was just rebuilding it from scratch every time we unroll a loop. It worked fine until now, but when we slightly changed our thresholds, we now started to unroll other loops. And we hit the problem when we hit the case when it was too slow. Generally speaking, it's usually an indication of a problem if a loop pass starts to look at the function scope or at the outer loop scope. And that's exactly what happened. We had a case where we had one function with huge loop nest containing like 200 loops inside, and we unrolled every loop of this nest. But every time we unrolled the loop, we also started to recompute dominance tree for the entire function. So this approach had approximately quadratic behavior of number of loops, and you can imagine how slow it was. Luckily, DT dominance tree can be updated locally when we unroll, and it's not very difficult. So let's look at an example to see how it can be done. In this example, we have a simple loop with one extra exit from block C, and a dominance tree for this loop would look like this. So we have an entry A that dominates all blocks in the body of the loop, and predecessors of exits dominate the exits. So let's imagine that we need to unroll this loop by a factor of 2. So its control flow graph will start to look like this. Now we clone some blocks and we need to compute dominators for them. So let's do it step by step. And let's start from the cloned entry A star. The new entry the cloned entry only can be reached through the original edge coming from the block D, which means that D is the new dominator for A star. Now, A star is the only entry to the cloned body, which means the dominant structure of the cloned body replicates the dominant structure of the original body. So we can copy it as well. Now we only have to compute dominators for exits. It's a bit more interesting because we actually introduced new passes leading to exits. For instance, exit E now can be reached from both C and C star. So to compute its dominator, we need to find nearest common dominators of all exits, which in our case happen to be A for E and D star for F. And now we are done updating the dominance tree for this part of the control flow graph. And please note that we didn't even look at the rest of the function at other loops, and this way we completely get rid of that quadratic complexity that we had before. So instead of full recomputation of dominance tree for the entire function that we had before, we now have a cheap local update of the dominance tree. That was one example of technical debt that we met in our work. It worked fine until we tried to change something in the other pass, but since we exposed this issue, we had to fix it before we could proceed. Unfortunately, it was not the only issue, and as we discovered a bit later, we also did the same for LCSSA form. So every time we unroll the loop, we rebuild LCSSA for the entire function. To be exact, we recomputed for the loop nest we worked on. And unfortunately, for LCSSA, it's not always that easy to update it locally. So let's see why this is the case. And let's start from the definition of LCSSA. It stands for loop closed SSA form, and a loop is considered to be in LCSSA form when all values defined in this loop are only used inside the loop or in fee nodes and its exits. And these exits are dedicated for this loop, which means that they don't have predecessors other than from this loop. Why is this useful? LCSSA makes it easy to update SSA form after we make some transformations on control flow graph with the loop, within the loop, because it makes it local to the loop. So let's see what happens with LCSSA when we unroll a loop. Let's go through a couple of examples. So this is the first one, and here we have two loops, and the control flow graph for them will look like this. We have an inner loop with two middle blocks and an outer loop containing all the blocks. And now there is a question, is this in LCSSA form right now? The answer is no, because we have the value b defined inside the inner loop and used in the outer loop. And it's not a phi node, which is a requirement of LCSSA. So to convert these loops to LCSSA form, we actually need to insert a phi node there. And now it's a valid LCSSA form. So what happens if we unroll a loop? For the sake of example, let's assume that we want to unroll the inner loop, and for simplicity, let's assume that it iterates only once, so unrolling would just remove the back edge. So let's see what happens if we do this. Now we have a single loop, and all definitions and all uses are inside this loop. That means that by definition of LCSSA, it is correct LCSSA form, because we don't have any uses outside of the loop. So we unrolled the loop, and we didn't even need to do anything to preserve LCSSA. It was just fine. That's something we like. It's good when we have nothing to do. But unfortunately, it's not always the case. In some examples, like in this one, unrolling can actually break LCSSA. So let's see why it happens. So again, control flow graph look similar to the previous example, but here we also have an early exit from the inner loop. The inner loop contains two middle blocks, and the outer loop again contains all the blocks. So now again, let's assume that the inner loop iterates once, so when we unroll it, we just remove the back edge. And the back edge here means goes from the if back to the while loop, to the inner while loop. So when we remove this back edge, we basically remove the if from the inner loop and unconditionally return. So after unroll, it would look like this, and we actually can use if instead of the while in this case. And this is what we get after unrolling. But now we get a definition A from the outer loop, which is used in the block which fall out of the outer loop, which means that LCSSA is broken. And please note that we unrolled the inner loop, but managed to break LCSSA for outer loop. That is, to fix it, we probably need to also check outer loop, which is an indication, which is a potential indication of a problem, as I said earlier. So what can we do about it? Not much, unfortunately, for now, but at least we can avoid recomputation for the cases similar to the first example. And luckily, it's most of the cases when we talk about real programs. So instead of full recomputation and full unconditional recomputation that we had before, we now first check if we actually broke LCSSA and only then rebuild it. The condition for rebuilding LCSSA is that after unrolling, some blocks fall out of outer loop, and only in this case. Along with the fix for dominance tree that I mentioned earlier, this fix gave us up to 50 times faster compile time for some cases, like the case I mentioned before with the huge loop nest, which was pretty cool. However, we still need to realize that we still have some technical debt here. We still can hit nonlinear behavior if we are getting unlucky and all our loops have early exits or something like this. So when we did this, we also wanted to check if we actually understood the problem correctly and we actually recompute LCSSA every time we break it. So to check ourselves, we added a verifier right in the end of loop unrolling. Of course, it immediately failed. That wasn't a surprise. What was a surprise that that it also was broken even before our pass started. That was an indication that some other pass doesn't preserve LCSSA, though every loop pass is supposed to do it. And now it was, again, our responsibility to fix it if we wanted to proceed with our feature, even though the feature was correct. So to find the offending pass, we decided to use loop pass manager and to run verify LCSSA after every loop pass that we have. So our pass structure started to look like this. And we found lots of bugs. We found bugs in invar simplify, in loop unroll itself, in loops simplify, in IRC, and in other passes. These bugs are fixed now, but there are some outstanding. So we still have some work to do. And we were very happy that we found them now, because every one of them could have led to a nasty miscompile, which we would spend like at least a day at just understanding what's going on. And now we found them all for free. So inspired by these findings, we decided to add even more verifiers. So now we are working on, we actually fixed the verifier for loop info, which was not ideal. And also we tried to enable verifier for loop simplify. The verifiers are in place, but we cannot enable them because they fail. So there are still some bugs to fix first. But still, it's the road we want to take. So this was my small example of how we started to work on a seemingly easy task of just flipping a default value for our optimization. But it ended as a very long battle with bugs all over the passes. And I think every one of us has a story like this to tell. So what can we learn from it? I would like to take several points here. First of all, we need to use more verifiers. More verifiers is better than less verifiers. And I'm not talking only about the existing verifiers. We also need to think about the new code we introduce. We need to think about what we can verify there. I think it might be reasonable, for instance, to require all analysis passes to have a verifier. Maybe we should even make this a developer policy. We also need to inspect the existing analysis for the fact that they have verifiers, and if we have them, that we run them at least from time to time. The next point I would like to make might sound a bit trivial. We need to test more. But here, I don't mean that we need to run more test suites or run more iterations in our testing, which is, of course, great if we can do this. But rather, I would mean here that we need to actually consciously try to break our compiler. Using non-standard thresholds for optimizations is one way to do it. For instance, it was very helpful in my case. Using test generators is another promising way to do this. A lot of bugs that we fixed this year were found on the programs generated by C. Smith. And there are, of course, other ways. We just need to be more creative here. And the last point I would like to make is don't afraid about technical debt. Remember about it when you start planning your work on a new feature. It will probably take more time than just implementation of your feature. You will also have to fix other passes as well. And so don't expect that your work will be localized in your pass. You will probably have to look into other passes as well, but don't be afraid of it, but rather embrace it. And actually, it's very fruitful to be proactive and try to expose the technical debt before you unexpectedly hit it. So let's together work on reducing technical debt in our code base. It's not possible to remove it completely, but if we keep its level low, then our code would look cleaner, we will be happier, and we will get less bugs in the end. So with this, I would like to end the talk. And before we proceed to questions, I would like to say thank you to everyone who contributed to these efforts and to you for attending the talk. Thank you.
Any questions? We have a microphone in the middle.
Work. I have a question about the LCSSA. You said that if you detect you need to rebuild it, then you run it again. But do you need to run it for entire function or only for the loop that is outer loop or any nested loop in this branch?
Yeah, that's a good point. And actually, we do rerun it for only the loop, the outermost loop we touched.
Okay, so if there's another loop nest, then
we don't touch it.
Okay, thanks.
I have a question.
No. Now it works.
Okay, thank you. So the idea of having more verifiers, more verifiers better. I agree with the main idea. But did you measure the overhead each verifier adds?
Of course, they're expensive, especially some of them. Like verifier LCSSA, I ran it for the entire function. But the thing is that we don't have to use them and usually we don't use them in release compilers. So they usually have a flags that allows you to disable them. So they just gives you an opportunity to find bugs. They don't impose you the burden necessarily. I know that now we have something enabled by default, and I know some complaints that they are slow, and we are working on it. But it's a trade-off, and I agree that we need to put expensive verifiers under a flag. But the danger here is that we never run them after it. And what's the point of having them then? At least we need to set up a bot that will run, I don't know, LLVM test suite with all verifiers on. Yeah, that's my take on it.
Thank you.
I have a question about LCSSA and having to go all the way up to the outermost loop. It's currently only the variables that are defined within the loop have to be used within the loop. But if you were to require the converse as well, that everything used in the loop had to be defined either in the loop or in the preheader, would that allow you to maintain that form more readily?
I see your idea. I think it would help, but it would also create more cases when we break it and actually have to do something to preserve it. In general, there is like an ultimate extreme case of LCSSA where in the beginning of every basic block you have fee nodes for every values used. If we do this, then by definition we don't break LCSSA in any case, but that creates another burden that more than half of our instructions would be fee nodes. So it's a trade-off, and currently we have what we have, but we can reconsider if it proves to be useful.
Hi, I'm just wondering whether or not you have any tooling to contribute or to help people find nonlinear behavior in their passes or downstream code.
I don't have any special tooling suitable for other cases other than I had. So I don't think it makes any sense to upstream it. It's mostly like hackish scripts that I have. And usually it requires test by case by case view. But it would be good if we can actually figure out something general, but I haven't. So
further questions?
When you were looking at compile time regressions over the past 2 years, I'm curious, did anything stand out to you as being an area that would need the largest amount of work right now to get us back, specifically in the LLVM backend, get us back to 3.7 levels?
Well, frankly speaking, I haven't looked into all the regressions yet. And I expect some of them are not fixable at all. Like when we introduce new features, we usually get overhead. That's something that we can't change. And some of the features can be at least disabled, like a new optimization we can disable for O0 and OS. But if we, for instance, introduce new warnings in front end, it's a useful feature, but it takes time to produce useful warnings. So some of them are not fixable. Speaking of actual stuff that we can look into, I mostly know problems with loop unrolling and related stuff. And I hope I fixed most of them by now. But yes, if we speak about backend, there are better guys to talk to, like Matthias, for instance, I guess. Thank you.
More questions?
Well, there are optimizations that have limits for the complexity. Like when we reach some point, we stop the analysis and do whatever we can do at that point. What do you think about introducing this for all loop optimizations and introducing like an optimization set which will take us in account, like for a fast compilation?
I think that's something we want to have eventually. I don't know how we can implement it in a maintainable way yet. I mean, just having cutoffs, we usually have them already, but there is always a case when you want to just increase it by 1 and get it, and it's not a general way across all optimizations. So in general, I do agree that we need to have some budget that we can spend, and we need to allocate it across different passes somehow. But currently, there is no efficient mechanism to do this, only specific for every specific pass. So if you have ideas, please, you're welcome to contribute.
Yeah, so basically there is already these limits in almost all the optimizations, but there is no like one value that controls everything. We can control them separately in the each optimization, but there is no point to control all of them. So it's like a...
Yes, and on top of that, also, for instance, loop unrolling has a threshold for the biggest size of the loop that we can unroll. But when I introduced this new feature, it might just spend more time analyzing the loops. And the original threshold wouldn't control it. We just slow down, though the threshold is the same. So we also need to take this into account somehow. So yeah, there are a lot of stuff to do.
Any more questions? We still have 2 to 3 minutes.
Not a question, but about a comment. So this is not really a question, but related to the compilation time reductions. So one of the things I noticed by looking at how the path manager works and how the analysis dependency is satisfied. So what happens is that when the transformation wants to work on something, then even before looking at whether the transformation has any opportunities to work on it, the path manager tries to satisfy the prerequisite analysis, right?
Yes.
So it would be nice if we can actually cook up on some solution to go through whether there is any need to even satisfy the prerequisite before running the analysis for certain transformations. Because if there aren't any opportunities inside, then there aren't any reason why we have to satisfy the prerequisite, right?
Yeah, true.
As far as I know, the new path manager will compute analysis dynamically or lazily.
Oh, so
But
that works in that way?
I think that is planned,
Okay, great.
as far as I know.
Hope it delivers.
So the problem that is, how do you know you're going to change the IR before you have a chance to run on it? And if you have a chance to run on it and you are ready with the IR in your hand, and you created a new loop or a new basic block and you're writing stuff and say, oh, this is identical to the previous one, I can throw away. Which means if you need to run your pass to know if you're going to do the analysis, and then you say, oh, I'm going to run my pass and I ran it and I'm going to change it, but wait, I need to go back and then rewrite all the analysis and then you need to pass back again. But now, because the analysis was rerun, you don't have the same dependency anymore. And now you run it again and say, oh, I can't change the IR anymore. And then you go back and say, oh, just, so it's a loop that you can't get in. So the only way to do this is to have some guess, and the guess is the analysis pass. And when you say, I depend on this analysis and it hasn't been invalidated, then it's because it doesn't matter to you, right? So the analysis pass that you depend on is the guess. So if instead of adding just all the analysis that you do, you can add an analysis which is, do I guess if this we're going to change or not? And then you move this, so with the new pass, that you can dynamically add those things and filter them out. If you add your own pass which says analysis is compulsory to my pass, but it's a very cheap thing, I can just put it in here, and it's going to just try and guess, and then and you will always pass. Right, and it marks your basic block with something special in it. But then again, you start marking things, and it's not a simple answer. It's not something like, oh yeah, I know I'm not going to change anything. Let's just go back. You can't know this until you actually do it, and when you do it, the analysis is different. So with the verifier thing, we could have a similar thing. So the way you were describing, like if really needs to change. Right? Is that something you did on the pass itself, or is this something that the pass manager knows?
This time it was on the pass itself.
Because if you say something, oh, my pass invalidates LCSSA, my pass invalidates this and that, and then the validation becomes a part of the dependency in the pass manager rather than something specific on your pass, even if it's separated from the pass manager.
But that returns us to the first problem that all the passes have different sets of preserved analysis and required analysis. Mm-hmm. So we can end up with loop unrolling split into a separate loop pass manager, which is correct. Other passes they don't break LCSSA, so we can run them all together and then run loop unroll independently. But that's not what we want. We want to unroll inner loops before we run other passes on outer loops.
Yeah.
So yeah, but to the point of avoiding computing analysis, in general case, you're right, but there are some specific cases. For instance, if you don't have loops, you don't need any loop-specific analysis. Though they probably don't have much time if you don't have loops, but maybe you don't even need dominance tree in this case. Mm-hmm. Oh, you probably need it, but just as an example. You can probably just shove off a lot of analysis if you know that you are not going to vectorize anything, you're not going to unroll and rotate anything.
Yeah.
So stuff like this can be trimmed.
Okay. Let's thank the speaker again.
Thank you.